Hello again, and welcome to Lesson 5 on this series on waves. In this lesson we'll be having a look at transverse and longitudinal waves, and the differences between them. By the end of this lesson, you should be able to give a definition of a transverse wave, give a definition of a longitudinal wave, and give examples of both transverse and longitudinal waves. We're going to start with transverse waves. According to the Oxford English Dictionary, the word transverse means situated or extending across something. And so a transverse wave is when particles vibrate at 90 degrees to the direction of the wave. In this animation, we have a wave moving from left to right, horizontally. A particle on the wave is represented by the yellow dot. You can see it moves up and down vertically at 90 degrees to the horizontal plane. So as the wave moves from left to right, particles in its path move up and down. This is a transverse wave. Waves that involve the motion of particles are sometimes called mechanical waves. Water waves are mechanical waves, and so are guitar strings when you pluck them. You can see that as the wave moves horizontally, particles in the wave's path move vertically at 90 degrees to the direction of the wave or the direction of the energy. Light waves are also transverse waves, even though light waves don't involve the motion of particles. Light waves are electromagnetic waves. They're made up of oscillating or vibrating electric and magnetic fields. The red wave, represented by the letter E, is the electric field. You can see here that it's oscillating or vibrating in the vertical up-down direction. The blue wave is represented by the letter B. It's the magnetic field, and it's oscillating in the horizontal plane. But both of them are showing this very distinct transverse shape. Water waves and light waves are both examples of transverse waves. So what about longitudinal waves? In a longitudinal wave, particles vibrate along the same direction as the motion of the wave, or the transfer of the energy. The word longitudinal means running lengthwise rather than across, again according to the Oxford English Dictionary. We have an animation here of a speaker. You can clearly see that the energy or the wave is spreading out from the speaker towards the edge of the screen. But have a look at one of the particles. Focus on one particle and you'll see that it vibrates or oscillates around a fixed point. None of the particles move outwards with the wave. They just vibrate along the same direction as the wave. In these videos, sound waves are passed through a glass tube, and at the bottom of the glass tube there are polystyrene balls. The sound waves inside the glass tube produce areas of high and low pressure, and you can see the classic longitudinal wave shape form in the polystyrene balls. The distance between these squeezed up areas and stretched out areas is half a wavelength, and it varies as the wavelength of the sound changes. Sound waves are examples of longitudinal waves. Lastly, I would like to go over an example question. This one's from the 2018 SQA past paper. You can find the link to the past paper on the screen. It says that sound is a longitudinal wave, and it gives you a diagram. You can see in the diagram that there are areas that are squeezed together and other areas that are stretched apart. This is a classic diagram of a longitudinal wave. The first question says state what is meant by the term longitudinal wave. I'll give you a minute to do it. Pause the video. So a longitudinal wave is when particles on the wave vibrate along the same direction as the wave. The official marking scheme from the 2018 paper allows answers such as particles vibrate or particles oscillate in the same direction as the energy, or particles vibrate or oscillate in the same direction as the wave. Please note that it is not acceptable to say that particles move in the same direction as the wave, because the particles vibrate back and forward around a fixed point. They don't move with the wave. The next question is one that I've noticed quite a few pupils struggle with. It asks you to determine the wavelength of the sound wave. Take this opportunity to pause the video and have a think. Okay, so a wave is a repeating pattern. So you see those areas where the waves are squeezed together. The distance between each of those areas is one wavelength. So how many wavelengths do we have taking up the 0.272 meters? We've got 1, 2, 3, 4. This means that we've got 4 complete waves taking up that distance. So one wavelength is 0.272 divided by the 4 waves to give us a wavelength of 0.068 meters. The last question asks us to calculate the frequency of the sound wave in air. You should know by now that to calculate a frequency, it's the speed divided by the wavelength. From a previous video, the speed of sound in air is 340 meters per second. We calculated the wavelength in the previous question too, so we know both of these values. That gives us 340 divided by 0.068 meters to give us a frequency of 5000 Hz or 5 kHz. So, by now, you should know that a transverse wave is when particles vibrate at 90 degrees to the direction of the wave. You should know that a longitudinal wave is when particles vibrate along the same direction as the wave. You should also be able to state that sound is a longitudinal wave and that light and water are examples of transverse waves. Thanks again for watching. Please like and subscribe, and I'll catch you next time. Bye.